Hello everyone, welcome back to my YouTube channel. This is Kirtana, currently pursuing my BE in Electronics and Communication at Sri Venkateshwara College of Engineering, Bangalore. Today I am back in front of you after a long time. Today in this presentation I will be presenting you all a topic related to physics, and the topic is numerical aperture and its derivation. Before moving on to the main topic, let me all give you a small introduction of numerical aperture. So, the introduction of numerical aperture is numerical aperture expressed as NA is a key concept in optics that measures the light gathering ability of an optical system. NA, that is numerical aperture, determines the resolution, depth of field and light gathering ability of a microscope objective. Now let's look into the definition of numerical aperture. The numerical aperture expressed as NA as told before. The numerical aperture of a fiber is defined as the sine of the largest angle of an incident ray can have for total internal reflectance in the core. Now let's look into the expression for numerical aperture, that is the derivation of numerical aperture. Let us consider a light ray AO incident at an angle theta enters into the fiber. Simultaneously look into the figure which helps in better understanding. Here the incident light AO enters into the fiber at an angle theta. Let theta 1 be the angle of refraction for the ray OB. Here we can see that theta 1 is the angle of refraction for the ray OB. The refracted ray OB incident at an critical angle is given as 90 minus theta 1. At B grazes the interface between the core and the cladding along BC. In the figure we can observe both the core and the cladding. The 90 minus theta 1 at B grazes the interface between the core and cladding along the line BC. If the angle of incidence is greater than the critical angle, it undergoes total internal reflection. Thus, theta is called the waveguide acceptance and the sine theta is called the numerical aperture. Now, let's see how to derive an expression for numerical aperture. Let me consider Snell's law at point O. I am considering Snell's law at the point O. So, it becomes n naught sine theta naught is equals to n1 sine theta 1. Let's consider this as equation number 1. Again applying Snell's law at point B. Here I am showing you the figure again. I am applying the Snell's law at point B. So the equation becomes Ni sine 90 minus theta I is equals to N2 sine 90 degree. Sine 90 minus theta is cos theta, hence it becomes Ni cos theta I is equals to N2. Let's retain cos theta I on the left hand side and let's shift Ni to the right hand side, that is to the denominator. So it becomes cos theta I is equals to N2 divided by N1. Let's consider this as equation number 2. From equation number 1, sine theta naught is equals to n1 divided by n naught sine theta I. In place of sine theta I, we are considering it as root 1 minus cos square theta. So the expression becomes n1 by n naught root 1 minus cos square theta. Let's consider this as equation number 3. Using equation 2 in 3, it becomes sine theta naught is equals to n1 divided by n naught root of 1 minus n2 square divided by n1 square. Let's consider this as equation number 4. Now the numerical aperture NA is equals to sine theta naught is equals to root of n1 square minus n2 square divided by n naught. If the surrounding medium, this is a condition, if the surrounding medium is air, n naught is equals to 1. Then numerical aperture is equals to sine theta naught is equals to root of n1 square minus n2 square. For any angle of incidence equal to theta I equal to or less than equal to theta naught, the incident ray is able to propagate. That is theta I less than theta naught, sin theta I less than sin theta naught. In place of sin theta naught, we are considering n1 square minus n2 square. That is sin theta I is less than root of n1 square minus n2 square. Hence, sin theta I is less than numerical aperture, the condition for propagation. Coming to the last part of the video, let's look into the applications of numerical aperture. The first one is numerical aperture is crucial in various fields such as biology, material science and semiconductor industry. In material science, numerical aperture determines the ability to resolve small features in materials. In biological imaging, higher numerical aperture are essential for detailed imaging of cellular structures. Thank you for watching. Please do like, share and subscribe my channel.